Good morning, ladies. Today we are looking at some more electric field calculations, and we are looking at calculating the electric field due to more than one charge. My first example over here that I want to look at isn't from the textbook, so let's just take a look at this. Two charges Q1 of positive 3,5 nanocoulomb and Q2 of positive 4,5 nanocoulomb are separated by a distance of 50 millimeters. What is the electric field strength at point X, which is positioned 15 millimeters from Q1 and 55 millimeters from Q2? So take a look at the diagram that I've got over here. I have converted nanocoulomb to coulomb. So here's charge 1, positive 3,5 times 10 to the power of negative 9 coulomb. Here's charge 2, positive 4,5 times 10 to the power of negative 9 coulomb. This is point X, 15 millimeters from Q1. I've converted to meters by dividing by 1,000. And it is going to be 35 millimeters from Q2, and I've converted that to meters as well. So now I want to know the strength of the field at point X. And the strength of the field at point X will be a combination of the field that surrounds Q1 and the field that surrounds Q2. So firstly, we have to calculate the strength of the electric field over here as a result of Q1. So for a second, I forget that Q2 is there, and I say I want the strength of the field a certain distance away from a charge. So this is the formula that I am going to use. E is equal to KQ over R squared. K is Coulomb's constant. The charge, and I don't write down the sign, is going to be 3,5 times 10 to the power of negative 9. And the distance is the 0,015, which I must remember to square. And this is the answer that I get. And the unit for electric field strength is newtons per coulomb. But what is the direction of the field here as a result of Q? So over here, I just did a little drawing. So there's Q1. It is a positive charge, so this is what the field lines will look like. And the direction of the field here at point X is going to be to the right, because I still use my positive test charge to find the direction of the field. And if I put a positive test charge here, it will be repelled by the positive charge and it will move away from the charge. And that is how I know the field as a result of Q1 will be to the right at point X. But then I must also work out the strength of the field as a result of Q2. So now I forget about Q1 and I say I want electric field strength a certain distance away from a charge. So E is KQ over R squared, Coulomb's constant, the charge, the distance squared, and the answer that I get is 3,361,22 newtons per coulomb. Now, what is the direction of the field going to be here as a result of Q2? So there's Q2. It carries a positive charge. The field lines would look something like that. And the direction of the field will be away from Q2. So at that point there, the field as a result of Q2 is going to be to the left. And as we said, the strength of the field here is a combination of the electric field around Q1 and around Q2. So now I have to take a look at my two answers and I have to find the net field. Here it's to the right and here it's to the left, so it's in opposite directions. So the electric field strength will be the difference between the two. And just like we do vector calculations, I always just say the big one minus the small one in the direction of the big one. So that is how I know that it's going to be to the right. And if I say that minus that, this is the answer that I get. So that will be the electric field strength at point X as a result of Q1 and Q2. Okay, then another worked example, and this one is from your textbook, and this you'll find on page 194 in your book. Consider the arrangement of charges shown in the diagram. QA carries a charge of positive 1 coulomb, B is negative 2 coulomb, and C is positive 6 coulomb, so I don't have to convert. Calculate the net or resultant electric field due to these charges at point P, which is 1 centimeter above charge C. So this is what the diagram looks like now. So here's charge C, positive 5 coulomb. Point P is a centimeter above charge C, and this is where I want to find the strength of the field. So I've converted centimeters to meters by dividing by 100. Here is charge B, negative 2 coulomb, and the distance between these 2 centimeters, which I've converted to meters. Here is charge A, positive 1 coulomb, and the distance between these two given as 4 centimeters. Now, the strength of the field here at point P will be as a result of the field around C, the field around B, and the field around A. So I have to do 3 calculations. So for my first calculation, I ignore B and A, and I say I want the strength of the field a certain distance away from a charge. So E is equal to KQ over R squared. Coulomb's constant, the charge is the 6 coulomb, and the distance is the 1 centimeter, which I've converted to meters, and that is the answer that I get. And if I draw the field around charge C, which is positive, at that point there, in which direction is it going to be? It's going to be upwards because it's always away from a positive charge. But then I also have to find the strength of the field as a result of charge B. So then I pretend that C and A, that they're not there. So I want electric field strength a certain distance away from the charge. So the charge is the 2 coulomb, and the distance is 1 centimeter plus 2 centimeters. So that is what I did over there, and that is how I got 0,03 squared, and that is the answer that I got there. Now, charge B, this one over here, carries a negative charge. So what is the direction of the field going to be over there? It is going to be towards the charge. It is going to be downwards, because I always look at what a positive test charge will do. And then lastly, I have to find the strength of the field as a result of charge A. So it's as if that one and that one isn't there. So it's electric field strength, a certain, let's just do that, electric field strength, a certain distance away from the charge. And what is the distance going to be now? It's 1 centimeter plus 2 centimeters plus 4 centimeters. So that is where I got the 7 from, which I converted to meters. And that is charge A. The answer that I get is 1,84 times 10 to the power of 12 newtons per coulomb. And what is the direction going to be of the field here around charge A? A carries a positive charge, so it is going to be upwards. So now I've got the field as a result of A, the field as a result of B, and the strength of the field as a result of C, and I have to find the net field. So I've got up, down, and up. So if I add the 2 ups together, it's more than the downward force. So I know the resultant force is going to be upwards. So over here, I said that plus that minus that, and that is the answer that I got. And always remember, electric field strength is a vector, so we need to specify direction. Okay, then exercise 9.5 on page 195 of your textbook is where you can go practice some of these questions. And since this is the end of the section, there is also chapter 9 revision questions on page 196. And I'll give you a day to do that. So you can work on that on Wednesday, and on Thursday I will post the answers. And then maybe what we'll do this week, on Monday only, next week, I will start with the next section, and you can use Thursday to mark the revision questions, and then Friday you can contact me if you have any questions about this section on electrostatics. Thank you, ladies.